In this video, I want to take a look at the derivatives of vector valued functions. So here's the definition. Given a vector valued function r of t, we define the derivative of this function as, here's a couple different notations. First of all, dr dt and r prime of t, right? Very similar notation to what we had for functions of real numbers, right, with real outputs. And now the derivative is the limit as h goes to 0 of r of t plus h minus r of t all over h. This looks a lot like the derivative we had in Calc 1. The only difference now is that the numerator here is a vector function minus a vector function. So this is a vector in the numerator. And when you then multiply by 1 over h, you're multiplying by a scalar. The result is still a vector. So the derivative of a vector function will still be a vector function, be a different vector function. Now, I want to point out that this derivative, it works in R2 or R3, right? 2 dimensions or 3 dimensions or even higher. I didn't say where I was, but it looks the same. Figure out what r of t plus h is, subtract r of t, divide that whole thing by h, take the limit as h goes to 0. Okay. Now let me show you a picture of what's going on here. So what I have here is a curve described by the vector function r of t equals, definition is here, where am I plotting? Parametric plot, f comma g. So f is t cubed minus t, and g is negative t squared minus 0.5 times t squared minus 4. So that's my vector function. I have two vectors drawn in here. The origin is right here, and I'm drawing the vector from the origin to the point r of a, where a is, in this case, 1.5. Sorry, 1.15. And then this other vector is r of t plus h, where, sorry, a plus h, where h here is 0.05. I can change these sliders to change what h is. Right, this one changes what h is. This one would change what point on the curve I'm looking at, what a is. This one is just out here where I can see it kind of nicely. Now, when you look at r of t and r of t plus h, and you subtract them, r of t plus h minus r of t, that would be the vector in between here. Right? If I then divide that by 1 over h, of course h is going to be getting small, and when you're dividing by a small number, it's like multiplying by a big number. So this vector in between r of t and r of t plus h will be getting small, but then it will be scaled up to be something big. So this is it scaled up. This is precisely calculated as scaling it up by h, or 1 over h. So what I want to look at is what happens when h goes to 0. Well, h is currently at 0.207. So if I grab hold of this and make it smaller, there's 0.16815, 0.13. All right, and you can see what's happening is that that tiny little vector between them is getting closer and closer to a tangent vector. And in fact, when you get to 0, you're looking at tangent vector. You can also do this from the negative side. Anyway, so right at that point where h equals 0, now technically right at that point, this vector is not defined because you can't divide by 0, but there's a limit as you approach, and that limit is this vector that you're looking at here. Right? It looks like a tangent vector. Right? It looks like it's just tangent to that curve. Likewise, I could just change what a I'm looking at. So at any point on the curve, when h is at 0, you're seeing that that derivative vector looks like it's tangent to the curve described by the vector function. So as in Calc 1, where we were looking at the limit of slopes of secant lines, this is now the limit of, not the slope of secant vectors, but it's actually the limit of secant vectors to give you a tangent vector right at the point on the curve that you're talking about. Now, this is all fine and dandy, but how do you calculate it? And this is where we have a very nice theorem. Suppose that you have your vector function described as f of t, g of t, k of t. I didn't use h here because I use h for something else, right? This is in R3. If it was R2, I would have just done f and g. But anyway, I claim that the derivative of this vector function is just the vector function where you take the derivatives of the individual pieces, right? And this is really not too hard to prove because of the way we add and subtract vectors and then how we multiply by a scalar. So by definition, this is how we take the derivative of a vector function. But I can say, well, if the vector function is fgk, so here's my fgk with t plus h plugged in, here's the fgk with t plugged in, and you're subtracting. Well, how do you subtract vectors? Well, you subtract component-wise. The first component's the second component's the third component. So there's the f of t plus h minus f of t, g plus h of t minus g of t, and k plus h, k, I'm not saying it right, k of t plus h minus k of t, and the whole thing is divided by h. Well, how do you divide by h? Well, that's multiplying by 1 over h, and I know how to do scalar multiplication. You multiply each component by that scalar. So I'm going to multiply each one of these x, y, and z components by 1 over h. And that's what I have right here. And now as I take the limit of this vector function, how do I take the limit of a vector function? Well, I take the limit of the individual entries, right? So take the limit of this one. That's f prime of t. That's from Calc 1, the definition of the derivative, right? Calc 1 again, the limit of this one as h goes to 0 is the derivative of g, and likewise this is the derivative of k. So how do we take the derivative of a vector function? We take the derivative of the components and make a vector function out of those. Here's a quick example. Here's my vector function. I've got t squared minus 3t. In the x component, I've got cosine let me change that. Cosine of t squared, comma, t e to the t, right? I had x's in there, and it's a function of t, not x's. So anyway, to take the derivative, oh, this is one thing, that if you really like taking derivatives in Calc 1, well, I've got good news for you, because here in Calc 3, each derivative is 2 or 3 derivatives, because you got to take the derivative of each component. So lots of practice on your Calc 1 skills. All right, what's the derivative of t squared minus 3t? Well, let's do t minus 3. What's the derivative of cosine t squared? There's a chain rule involved here. So it's going to be minus the sine of t squared times the derivative of t squared. So minus 2t sine t squared. And then this one's going to be a product rule. So t times the derivative of e to the t plus e to the t times the derivative of t. Notice I got commas in between. I'm not adding these up or anything like that. I'm just writing them all. The derivative of the first component is my first component. The derivative of the second component is the second component. And the derivative of the third component is the third component. I make them all into one big vector. And that is the vector function, which is the derivative of the one that we started with. And what we saw up above is that if you knew what the curve of this thing looked like, then this vector function would be telling you what the tangent vectors to that curve would look like. So there you go, derivatives of vector functions.